Next wave property we're going to talk about is refraction. It's the bending of a wave. Now, not that the wave itself physically bends, but as a wave travels from one medium to another, if its speed changes, its direction will change as well. Have you ever gone to the grocery store and you're pushing the cart along and you run into something on one of the tires and the whole cart swerves? That's because now that one tire is going slower because it's stuck on something, but the other tires keep going as fast as they were going to begin with. So the whole cart changes direction. Waves do this as well. We're going to talk about light specifically, but this isn't unique to just light. Sound does the same thing. For example, let's say we have light in air and it's heading towards water. I'm going to just draw a light ray. Now light is a bunch of rays, but I'm just going to draw one. As light continues and transmits through into the water, we know that the speed of the light decreases. The speed of light in any material is equal to the speed of light in air over the index of refraction in that material. Water, the index of refraction is approximately 1.33. So since the light slows down, it's like the shopping cart, the wheel getting stuck. It can't go as fast. So what happens, it ends up getting bent. The angles we're going to use are always going to be measured relative to the normal. The normal line, remember, is the line perpendicular to the surface. So this incident light ray, I'm going to call it theta 1, is bigger than this refracted light ray. Let's call it theta 2. Since the light slows down, it gets bent in towards the normal. So you end up with a smaller angle than what you started with. Which, that's why, as far as we're concerned, our brains just figure the light's following a straight line. So if you're standing in a pool, for example, your brain thinks the light's just going in straight, but because the light is actually bending, it'll get to the bottom of the pool faster. That's why everything looks shorter. That's why your legs look short and pudgy when you're standing in a swimming pool, is because the light reaches the bottom faster than what you would expect it to. I have a kind of a fun little picture that shows refraction. A turtle in a fish tank. I'll pass it around so you can see it better. That's what you're seeing in the water, but he's really floating above. So with refraction, where he appears to be is a bit different than where he actually is. We have a nice, easy relationship that relates those angles together. The relationship is called Snell's law. You take the index of refraction times the sine of the incident angle. That has to equal the index of refraction for the second surface, second material, times the angle in the second material. So in this case, N1 would be air. Index of refraction of that is 1. Sine of theta incidence, let's say this angle is 30 degrees, for example. So the incident angle would be 30 degrees. N2 is water, 1.33. Theta 2 we can find. Excuse me. So sine 30. theta 2, the angle in the water would then be 22 degrees. So it gets smaller. Whenever light is in a lower index of refraction transmitting through into a higher index of refraction, the angle will always get smaller. Okay. If your light originates in a higher index of refraction, so if you have light originating in the water, as it comes out, the angle will get bigger. But the relationship is still the same. The index of refraction times the sine of the angle in whatever the first material happens to be has to equal the index of refraction times the sine of the angle in the new material where the water happens, the light happens to be. Okay. So if the light originates in low, going to a higher index of refraction, the angle will get smaller. If the light originates in a smaller, originates in a higher index of refraction, going to a lower index of refraction, the angle will get bigger. Okay. Not terribly difficult. An interesting thing happens. The bigger this theta 1 gets, if we're in this higher index of refraction, the bigger theta 2 gets. At some point, theta 1 will be big enough to make theta 2 go to 90 degrees. That's called the critical angle. At that point, we get what's called total internal reflection. This is just a special case of our refraction. It only happens when you start in a higher index of refraction going to a lower one. Okay? It can't happen if you start in a low index of refraction going to a high. You cannot get total internal reflection that way. So you have to start in a high index of refraction in order to get total internal reflection. Snell's law still applies. We'll have the higher index of refraction times the sine of the angle in there, which is called the critical angle. And that will have to equal the index of refraction in the lower, and that angle will go to 90 degrees. Sine of 90 is just 1. So we get the sine of the critical angle is equal to index of refraction of the lower material, the lower index of refraction, over the higher index of refraction. For water, for example, we start in water with the light exiting out into air. Air is the lower index of refraction, so that's 1. Water is the higher index of refraction, that's 1.33. So the critical angle for water into air is 49 degrees. What that means is if this angle is 49 degrees, it'll make this refracted angle actually refract along this surface. The light will not exit the surface. It stays inside. That surface behaves as a mirror now. And this light actually ends up reflecting and following the law of reflection. Any angle bigger than this 49 is still a mirrored surface. Okay, it still just reflects off. and will follow the law of reflection. Now, total internal reflection, I have an example you can see. You can see the light bending off the sides and bouncing around. The reason it doesn't come out the end, why it's so spread out and not the fine laser dot like it was when it left the laser, is just because of the impurities within the plastic. This isn't by any means nicely made. So we can see the internal reflection up here, and it gets directed out of the end. You can get the laser coming out. It gets diffused a bit because of the impurities within the plastic itself. This is how fiber optic cables work. They're much thinner, and they're much more nicely made, of course. So Snell's law, pretty straightforward, not too hard to use. Total internal reflection is a special case of refraction. It only occurs if your light originates in a higher index of refraction and is exiting towards a lower index of refraction. This concept is why diamonds are so sparkly. Diamond has a pretty high index of refraction compared to air, so you get a lot of light that reflects internally within the diamond before it ever comes out. And that's why they're so sparkly. But if you've ever gone scuba diving, you actually, I don't know if you've ever noticed, if you have gone scuba diving, there's actually a window that you can see through. If you look too far either way, you can't see out of the water. But in closer, you can see out. Wherever the critical angle is, from there on out, it's reflecting, and so you're not seeing that. So it's kind of interesting that way.